Okay, so it's 1:30 now, and so um, welcome everyone, and thank you for joining. Today we have Dr. Sarah White, who is a professor at Plant and Environment Science Department at Clemson University. She has done a lot of work on water recycling and water quality in nursery and landscape, and a lot of extension work and big grants. So when I was doing my PhD, I was also working with Dr. White as a PhD student. So we know each other from a long time. But without further ado, I would like to hand over to Sarah, and yeah, please take it from here.
Okay, so y'all can see my screen and you got to hear the Southernism. That is probably my sole Southernism, the y'all, you all. It's a very inclusive term. And I must say that it was an honor that Dr. Pujal, and I apologize if I just butchered your last name because I usually call you by your first name, that
Yeah.
he invited me to come and talk to you all. This is something I'm passionate about, I love, and he was an amazing student in addition to the grant team. So realistically, if we think about water recycling, both for on-farm purposes and for the landscape industry, it gets critical and it gets to why should we do it? We probably have those, but the how gets to be a little bit trickier simply because of logistics. And if you haven't been doing it, you may have a lot of questions. So in terms of those, especially from the grower side, but frankly from the landscape side now, and I don't think it matters where you are in the United States, most of these concerns are come to mind when you consider recycling water. Realistically, why would one do it? Availability. If you're a grower and you need a backup source of water, and recycled water may be that source of water that gives you the option to continue producing plants or to expand your production area, or frankly, just to hold on and continue producing the plants that you're growing. And then when we're also thinking about availability, is it safe to reuse your water? And I think about you guys when I say, will it rain? Well, frankly, in the summer here in South Carolina, we always ask that question as well, as will it rain, and will it actually rain when we need it to rain? And then if we think about the recycling side of things, or when we start to, contaminants it's one of those first items that comes to mind that we're just asking, what's present? Do I have plant pathogens that I need to be worried about? Or if it's a landscape application of water, are there human pathogens that I need to worry about that could potentially impact health of humans, kids, or domestic animals? Algae and aquatic weeds are a big contaminant in recycled water, but also in surface water receiving runoff from the landscape or production areas. Pesticides and salts are also contaminants of concern, and so we'll talk about those sort of individually as we go along today. So the production challenges. If I think about this from a producer side and then think about it from an irrigation side, because I'm also the nursery extension specialist for South Carolina, so I tend to think more on the production side of things than the landscape side of things. But many of the production practices that impact how contaminants move on site or how plants grow, irrigation timing, irrigation efficiency, those kind of things, it cuts across whether you're talking about on-farm use or landscape uses, and the cultural practices of pesticide use or fertilizer application timing and plant diseases. So in the picture that you're looking at right now, that is actually sloped down hill, and you'll notice they have call piles of plants at the top of the hill. And so as water is applied and drains down, it drains through the next section of the nursery, and those plant pathogens that were in these plants that died sort of moved along and were able to infect the next batch of plants. And so they lost whole sections of plants because of that. So in reality, it's not just, am I applying water efficiently or am I applying fertilizer efficiently, but it's, did I do it at the right time? Or what have my practices that I didn't want to change because it's easier to do it one way than to change something? What have I lost? Is it money in terms of shrinkage of my crop? Or is it opportunity cost that I couldn't sell them for a premium, or that I didn't grow as many? There's just a lot of factors that sort of sort of connect with each other that really influence it. But realistically, our growers want to grow plants. Our landscapers want to have amazing landscapes to look at. And most of our consumers love to look at water within the landscapes. So how do you balance all of these differing concerns and desires of whether you're the grower, the landscaper managing it, the water management district figuring out who's going to get water, or the consumer who just says, I want to have a nice garden that I can go out and look at, or a nice city park or state park. And so when we think about growers, they apply water in different ways, some of which are more efficient than others. In this image, this is a boom spray system that's in a greenhouse. So the water that's applied within the greenhouse is typically captured and back into a cistern and recycled. But when you get to on-farm water, usually typically smaller containers are irrigated overhead, and those may or may not be efficient, and then the water runs off that production area. So I really want to sort of get you thinking about the types of water that you might, or I should say classifications of water, because this gets to be a pretty important issue when you think about recycling water, especially on-farm recycling and frankly landscape recycling, because I think some of these principles again are cross-cutting. So, and hopefully you can see the green lines, and I've actually picked good colors, but this first line, which is a green line, is operational water. And so operational water is any water that is applied to a plant or to a surface and then runs off and can run back into a retention reservoir. So it's operational water is something that it can be irrigation water, but it's also water that has hit its surface and come into contact with the contaminant, whether that's a sediment contaminant or whether that's pesticides or pathogens or anything else that might be undesirable. Now, when Sheetal and I were talking about stormwater and how to classify what we could capture and not capture, some of this gets down to classifications, the non-contaminated stormwater. So if you have a greenhouse and water's hitting the roof of the greenhouse and running off of that and not actually in contact with production areas, that water could legitimately be routed into a surface water and never come into contact with your production area and be perfectly safe to release. But it's also an ideal water to use to shoot back into your retention reservoir, because that really gives an opportunity for blending and mixing of poor quality water with better quality water, so that your water is actually, your plants have access to a better quality of water. Then there is sometimes when runoff just occurs, and that's when water comes off of a production area and does not go into a retention reservoir, but is rather discharged, whether it's into a surface water or whether it's infiltration into the ground. It's a water that's lost. And then you also have different sources of ground and surface water, which can be used to supplement irrigation or used to fill a retention reservoir, and can also help with blending and water quality issues. I say all that to say this. I'm going to talk about and use some of these terms, but really operational water and then irrigation return flow, which is sort of this green line where once irrigation is applied, whether it's to a landscape or to a production area, that water, if it can go into a retention reservoir, that's where we have the highest opportunity to recycle water, but also potentially recycle some of the nutrients that are within that water to better support plant growth, while also minimizing potential impacts to surface waters, which are usually not desirable because eutrophication and algal blooms are not something we want. But generally, when we're in the landscapes, we have different types of emitters, and out west, y'all tend to be more efficient than we are in the east. So you have some of the drip emitters, and again, gorgeous landscapes. But again, this gets back, whether the water's coming off of a production area or a landscape, it can get into surface waters. And if they get into surface waters, I believe it was a 2016 where Utah Lake had a pretty significant harmful algal bloom. And we're seeing those more and more often as water becomes more limited and we're not recycling water as much in some of our lakes and our reservoirs. We're seeing that nutrients are accumulating. And what happens when you have nutrients accumulate in some of these areas is the process of eutrophication, which is just frankly nutrient enrichment, where you have more nutrients added than the system is used to. And what typically happens then is you have algal blooms or excessive growth of aquatic plants and algae that can then, when they die, oxygen is consumed from the water column as they're broken down, and you can have fish kills or you can have the worst case scenario, harmful algal blooms. And so this is where runoff control and capture of stormwater and detention of that stormwater before it leaves a particular area so that sediments or other things have the opportunity to settle out, that is what is ideal. And then also, it's not only just are you managing the runoff, but then you have water available for recycling when and if it's possible. And that's where some of the intricacies of what you're allowed to do, I'm not sure of. So I'm just going to tell you, if you are allowed to do it and you can do it and you can get the right permits and things like that, this is how I would sort of go about it. But so if we think about availability of water for recycling, one of the first things I think about is how often is my reservoir going to get refilled by means other than just landscape runoff. So looking at y'all's drought map over the last year or so, you've had some pretty significant changes in from extreme drought to exceptional drought, then back to moderate drought, and maybe even some just abnormally dry. And so this gets to the how can you actually think about managing these reservoirs or your landscapes, frankly, when you don't know what the weather's going to be and you don't know when it's going to rain. Now, frankly, I think y'all might have had a bit of relief with the snowstorms and the rain that hit the rest of the West Coast. But in so saying, that's just a temporal thing. So how do you capitalize on the opportunities when you have them? And so that's when thinking about the infrastructure becomes really critical, because if you have the infrastructure in place to capture water, it is much easier to then capitalize on those instances when you do have rain, and so that you can ensure that you're capturing as much as you're allowed to do. And so, but when you do capture that, and especially if it's running off a land surface or a production area, there's going to be sediment carried in that water. And sediment is one of those contaminants we know we need to control it, but it's actually pretty hard to stabilize. I mean, it's not hard to stabilize. It just requires consistent effort and attention. But sediment, as sort of in this picture, coming in the inflow pipe, flowing down, you can just sort of see a sediment plume. And the issue with sediment is that it's sort of like a surface that if you have any contaminant that doesn't like to be in the water, it's going to bind to the sediment. So if you have a sediment added to water and you had a pesticide that was applied, chances are the pesticide sort of associates with that sediment. And then it has the opportunity to move and be carried. And so it could move off farm, which would not be ideal. Ideally, these retention reservoirs are designed to sort of capture and detain those contaminants. And then you have some sort of retention time, the longer that the water stays in there without being cycled or applied somewhere else, the better chances and opportunity there are for the contaminant to degrade. But then you can also have pesticides flowing in the water, but there's also contaminants of emerging concern. And if we think about landscape applications, or if you all have access to municipal reclaimed water, there are some contaminants of emerging concern that we can talk about if you're interested in, but think about like pharmaceuticals and personal care products, industrial or household chemicals, nanomaterials, and other things like that. There's just a lot of potential contaminants that we are not as sure about how to manage, but also we don't know what the potential impacts they have on the landscape. So retention reservoirs, again, just give you one more opportunity to sort of detain those and stop them from moving further within the landscape. And then the harmful algal blooms. This is one of the ones that I think we're going to continue to see growing of in your awareness, but also in, what's the word I'm looking for? How often they occur. They're going to occur more frequently. So they're going to be brought to our notice more often. Frankly, we just had one, and it's very unusual, in February at our botanical garden, where we found a harmful algal bloom. And this is just something where nutrients aren't limiting, algal species start to grow, and then you have a cyanobacteria that actually starts to grow, and a toxin can be released. It's not always released, but it can be. So we want to prevent algal blooms so that potentially we don't have the potential for the toxin to be released, because it can impact humans, it can impact domestic animals, it can impact livestock, it can impact wildlife who depend on those water stores for their survival. So it becomes pretty critical to pay attention and work to not have those issues or to manage these as well. So after all the doom and gloom of the contaminants, one of the good things about reservoirs is that it sort of helps provide water security. This is actually sort of a sediment forebay before a reservoir, and they cleaned out some of it, but you can just see the massive sediment in the center of this forebay that they've already removed, and they still have to come back and remove more. But forebays are what help us just trap sediment, and that's where you can lose capacity for storage. But because then you can clean it out. So if we have water security because you're storing water, we're also trapping contaminants. So if we can trap the contaminants before it gets into a reservoir, or the sediment before it gets into a reservoir, we're better off because then you have a smaller surface area that you actually have to manage. Because management is one of those critical pieces. Because if you don't plan for management or maintaining the bed depth or the pool depth within your reservoir, and you allow sediment to just sort of accumulate, you're going to lose some of your capacity for storage. And then if all of your best laid plans may not allow you to capture what you need to for storm mitigation purposes or for just water security purposes. And then again, contaminant trapping, we can trap agrochemicals, fertilizers, and pesticides. So we can retain those nutrients. If it's on, ideally, you want to recycle that water and reuse those nutrients so that you're not applying as much fertilizer. But if we're talking about within the landscape, think about this as a stormwater detention basis or a stormwater pond where you're actually using that pond as a sink to help manage those contaminants before it has the opportunity to get into surface waters or other large lakes that are more recreationally focused where humans could be impacted by that. And then again, plant pathogens. For some of the plant pathogens that are of most concern to growers like Phytophthora and Pythium, they have the propagules that travel in water actually have a finite lifespan, usually less than 48 hours. So if you can have a retention time longer than that before water is reused, chances are that most of those propagules will be dead and no longer able to infect plants. So even before any treatment is done, that water is less dangerous or less likely to be able to carry a propagule that can actually infest or infect the plant. So when we think about reservoir design, there's three things that we really want to think about. And on this slide, you'll see sort of the cutout, this land grant press. This is an article that if you're interested in figuring out design and some other considerations, takes a pretty deep dive into it. And the web link for this article that you can just download for free is there. But so you want to figure out how much water is going to enter the reservoir on a given time or over a given period, and how much will leave it, because that's going to give you your cycle time, like how fast will water cycle within that. But that got to point two, is how long will the water stay in the pond before exiting for reuse? Because the larger your pond that you can feasibly do within a specific budget, the more time for your treatment you will have, or the longer the hydraulic retention time, the HRT, how long water stays in there. So a longer HRT means that you have greater storage capacity, which also leads to greater water security, because you're going to have a longer period where you're not going to be overusing your water, and chances are you'll still be having water run back into it. So you may have a longer time to cycle water in drought scenarios where you may not have other sources of water coming to help fill that. And then depth to groundwater, that may not be as much of concern here, but I think it probably just depends on where you are geographically. In sort of some of our coastal areas, depth to groundwater can be less than 6 feet for us, or less than 3 feet. So it becomes reservoirs may or may not be actually a good management option in that case. But so when we really think about reservoir design, this is sort of just a side cut of what an ideal reservoir might look like. We have overland flow coming into it, or there may be piped in flow, just depending upon how water is moved and managed on farm or in the landscape. And again, so we have this option for a sediment forebay where the water has to fill to a certain point before it can overflow into the wet pond. And realistically, this is what you want. Something like this is what you want to see. Water comes in from the production areas on the left side and flows into this area where it's just allowed to detain and slow and sit for a while. And what's interesting about this farm, this is Altman Specialty Plants down in Lake Matthew, California. is they designed it so they could drive a track hoe or a backhoe a backhoe into this and scoop it out with a bucket and clean it out. So they designed it with good management practices in mind, or simple, so that it's easy to maintain. That you have one guy can go in there, pull out all the sediment that's accumulated, and then move it out and let it dewater, and then they can use it to fix roads or whatever else they may want to. But then they know that that sediment that's accumulating here is not going into their next pond to impact the storage capacity within that pond. So getting to storage capacity, when we're designing new reservoirs and thinking about that, it's really thinking about how big do you want it based on your production desires, or how many acres of production of your watershed are going to drain into a particular area. And then also, so there's that, but then there's also your storm events. So previously, when we talked about design of reservoirs, they were typically designed for to detain 2-year events. But in looking at it and looking at the frequency of some of these flashier storm events, and when I say flashier, they're greater intensity over shorter duration. So, an inch of rain in an hour instead of an inch of rain over a day, something like that. How water moves on site is going to differ dramatically just based on that. But what we're hoping and thinking that whenever possible, especially if growers are installing new ponds, new irrigation reservoirs to manage water, if possible, you're planning for a 2-year, 10-year, ideally 100-year storm to capture that water if you're allowed to do it. Because then that really gets to the water security and water, and increasing or making longer your hydraulic retention time, so you have longer for contaminants to cycle within the pond and be degraded before they're ever moved either into your irrigation system or moved off farm or released off site. So again, in that land grant press article really dives deep into this and gives you some of the thought and the perspective behind this. And this is based off of some of the NRCS recommendations. But this is just our best guess is our best information based on some of the predictions we're making for water availability, and also the desire of many of our growers to be very good stewards of the resources they have. So if they can capture water and then recycle it for a longer duration, then we're competing less for water, some of those potable water sources that other cities or users may need, and industrial users may need. So we have the reservoir, but what do we need to do to actually make that water safe to use? And so I've said this before, and I'm going to just keep harping on this one: pre-filter, sedimentation, sediment forebay, sedimentation areas. So this is another image of that sediment forebay that you saw, where the water that I mentioned earlier, where water can flow in, sediment can settle here. They can drive a truck in to clean it out, and then the water flows out and through sort of a wetland area before it goes into a storage pond. This image on the left is actually sort of as water flows down a hill, they sort of just built little check dams so that they could allow the grower could allow sediment to sort of accumulate and fall in behind these check dams before it flows further down the hill. There's a lot of little just interesting things that can be done with minimal expense that can make big impacts on limiting how sediment can move on site. And these same types of things can be done within the landscape and be landscaped features that are nice looking, but with a function and a purpose that we can then educate the public about. Okay, and so when we think about a reservoir and we think about wanting to reuse that water, pumping is one of those things that then becomes a really it's kind of critical issue. So many growers don't know that there is actually a good, sort of like a sweet spot where you want to let a pump intake be located within a pond, and they'll just sort of fix it at that bottom of the pond, or sort of that, if you were thinking about it and you're like, well, if I want to be really secure, I'm going to put my pump intake sort of to the bottom so I know I'm always in that wet pool. Ideally, that's not necessarily where you want your pump intake to be. And that really gets to down to sort of just the internal processes within the pond. There's a lot of sediment that settles to the bottom, and then you have a lot of aquatic life at the top. So ideally, you have sort of a floating pump intake that you have extended a set distance. Recommendations right now are about 3 feet, maybe a little bit more below the surface, but also off the bottom. You try to get it almost into the middle of the water column. And there's a lot of different strategies for this. There's not a right way or a wrong way to do it, but you don't want it at the bottom and you don't want your pump intake at the top. And realistically, this is why. It's because of disease contaminants within water. So if we're talking about like the plant pathogens, Phytophthora and Pythium, they are actually negatively geotropic, which means they like to move to the top of the water column. So if you put your pump intake well below the top of the water column and well below that sort of biologically active layer where all your algae will also accumulate, then you're not going to have as much issue or pressure from those type of contaminants there. If you have it 36 inches off the bottom, you're also probably going to have less issues with sediment fouling and issues with sediment being taken up within the pump. And then we also got to think about your pump intake location. Ideally, you put your intake as far from where the water enters the pond as possible. That's because, again, you're giving yourself retention time, the opportunity for water to be treated just by natural processes within the reservoir before it's ever reused. But then if you're using filters, don't put your backwash filter outflow right next to your pump intake, because your pumps are going to be working and your filter systems and the backwash are going to be working a lot harder because they're going to have to move more contaminants. And that was one of the things that we noticed with the picture on the right, is that our pump intake is sort of near this galvanized pipe here, and the backwash filter outflow is right next to it. So there's a lot of sediment and turbidity and other things that are just constant there that are making the pump work harder and the filters work harder. So you're going to also burn more energy. Also, for the pumps and maintaining the pumps, have them on floats. Ideally, you have a filter around the intake. The image to the right here is where they actually have an aeration system that blows and keeps all of the stuff that may be floating on the surface away from the pump intake, so that it doesn't actually come into the pond, so that there's into the pump intake, so that there's less work that the filters have to do. And then also limit algal growth in the pond as much as possible. And I'll talk about that in a little bit as well. So if we're thinking about sort of water management and contaminant management, grading your site is really important. You really don't want to see standing water. You really don't want to see algae growing in your roadways because the water has been standing on site so long. I would say I was shocked at this one. This is actually a Florida grower, so you will probably never see this where you're at. They had duckweed growing in their production areas. There was so much standing water, which is just not ideal. Although they are adapted to it, they actually have these nice little concrete blocks that they have put their plants on, so they're not sitting in the water, which just kind of just reduce how much water you're applying. Because over irrigation is one of those things that if you can manage how much you're applying, you're going to be leaching less nutrients out of your pots, or frankly out of your landscape. So if you can manage your irrigation better, then you're going to have less contaminants within your runoff to manage, which then means you have less that you have to treat. And that's the sort of the ideal feedback loop that we have. Even if a production area is well managed, when there's just consistent water applied, there may be issues with sort of this black sludgy looking organism, which is actually called nostoc, N-O-S-T-O-C. And it's really hard to control. It's not necessarily that it's something that's dangerous. It's just incredibly slippery. Like, so if you have people walking over it, it's slippery and they could fall, and, worker safety is an issue, but if it's in an area like in a garden center, I've seen it in garden centers sometimes, that can also be an issue of customer safety. And it occurs both on land and actually occurs in water as well. And the large patches can appear suddenly on moist paths, roads, roofs, and poorly drained ground. And it can be a little or a lot. So if we can limit standing water by sloping the beds and reducing irrigation rates, that goes a long way to solving many issues, but one of the least of which is how much fertilizer is actually being wasted or not staying where you want it. And when the fertilizer then moves from your production areas or from your landscape and into water, this is when you begin to have extreme issues with algae and aquatic weeds within the landscape. Riparian buffers, even around retention reservoirs that are man-made, are one of those things that are a practice that should be done because it's going to help you maintain water quality within your reservoir much more than anything else. It helps you. It's one of those simpler solutions, at least at the front end. Yeah, you may lose a little bit of production area, but if you're managing your water quality and you don't have to try to manage algae as much, it's worth doing. But there's also ways to think about this sort of in terms of, can you build two smaller ponds instead of one larger pond? The first pond that receives water tends to be the dirty pond, and the second pond receives the outflow from that first pond and tends to be a cleaner pond. So if you can sort of make connected ponds, that also helps with retention time and water quality in those ways. But again, algae is just one of those things that we're learning how to manage, but it's still not ideal. And it's and sometimes they're just normal green algae that are not harmful, but then sometimes it can be a species that could be harmful. But then you just transition even beyond just algae to the mosquito fern, which is this red looking organism here that actually can it fixes, I think, nitrogen actually, but you can see sort of a phosphorus. The red, it reminds me of a phosphorus deficiency, even though I don't think it's deficient in that. But then you also have duckweed, which is yet another problem. And I've seen both of these in waters, actually, I think in Utah. So it's just management becomes a sort of critical issue. So if one can, establishing buffers between irrigation ponds and production areas is sort of the first thing to do, because vegetation and just, again, distance and allowing for filtration through vegetation is critical there. You can pre-filter water before it enters the pond. That sediment forebay is also an ideal solution for sediment settling. Reduce nutrient leaching. So if you use controlled release fertilizers versus your either granular or just the fertigation, the liquid fertilizers. And you can move to some more efficient irrigation strategies, which I'm not going to talk about, but are feasible if they want to be questions want to be asked. And then the treatment chain, or just ponds that are connected to each other to help sort of increase retention time. One of the other things that is one of the more common practices that we're seeing implemented more often is that of aeration. Aeration actually does help to sort of limit how intense an algal bloom can be, even though you can sort of see sort of these bands of green within this pond. It is not that bright green, soupy mess that it could have been had there not been aeration within the pond. It's not going to, aeration does not solve your problem. It just helps to limit how easy it is for those algal communities to actually sort of grow and reproduce. So once you get your reservoir and you're sort of pre-filtering and all of that, are there things that can be done that don't involve chemical treatment? And the answer to that one is yes, there are ways that we can treat water for reuse that are pretty low tech, that allow us to clean the water so that it's safe for reuse. Floating wetlands are a newer technology that works. We've seen most of the work done in stormwater ponds and stormwater applications. I'll talk a little bit about that for production areas. Vegetated buffers are probably the most common practice that we have seen, and it's easy. It's sort of that bulletproof, it's been around for a long time, and there's a reason it's been around for a long time and will continue to be used. Slow sand filters are another great option, as well as sort of this carbon wall and the bioreactors. So filter strips and vegetated waterways are ideal because, frankly, you're just intercepting any water that is coming off of a production area. and you're filtering it, and you're giving the plants the opportunity to take up that water and to have sediment settle in. One of the nurseries in California had concrete lined ditches, and they actually grew a second crop of canna within these ditches. So they were cleaning their water, getting the sediment out, managing their pesticides while growing a crop that was then imminently saleable. And they actually had trouble keeping plants in the ditches because the plants grew so well that the marketers wanted to always sell them. So there are opportunities to use some of these treatment areas as secondary production areas. Again, the filter strip idea, where you're just having a place for sediment to settle, but also where all of the vegetation around that is also providing microbial habitat for microbial communities. And then you're getting much of your water treatment that way. Then there are also vegetated waterways. Depending upon how much water is coming off farm, or if you're not even recycling it, whether it's just treating it before it's leaving your site, vegetated waterways are one of these things that it's just sort of a very shallow marsh where you just have consistent water. It can also sometimes be more ephemeral if it's not all the time, as long as it's periodic enough that you're irrigating like once every 3 days, something like that, especially if it's really hot. There's different plants based on how consistent water will be, but they tend to work very well. And then you can also say capture your first half inch of rain during a rain event for treatment, while the rest of that water would then flow over and out without necessarily being treated. And that's kind of the design premise behind some of these vegetated waterways. Some of the other production areas, they've used barley straws, as there's supposedly a compound released by the barley as it breaks down that helps to inhibit algal growth. This operation was trying some of the canna ideas, but again, you got to keep a consistent flow in there. So they were having some issues, but sometimes it was working. Constructed wetlands are one of those things that if you have consistent water and it needs to be treated, you can design a system, and it can be sized just based on what contaminant you need to remove and whether you want to recycle or release the water. You can really have great impact for it's not inexpensive because it is taking land out of production, but it is highly effective because you not only have, whether you have a surface flow where you see water above the surface of the wetland like this one and it flows through there, or subsurface flow where it's more like a gravel with plants growing within that, and then the water is released subsurface, so you have less evaporative losses. Both work quite well as long as they're planted, because you want the plants for a carbon source for the microbial communities that do much of the work for remediation. And so your soils provide habitat for microbial communities. The microbes, think of denitrifying bacteria, help transform nitrate and help it volatilize into nitrogen gas, so it's released back into the atmosphere. They can also break down pesticides, the organic contaminants. The vegetation slows the water so that your sediment has a chance to settle out. And then the plants can also absorb some of the nutrients, metals, and some of the other compounds from the water to help clean the water. This is the example of a nursery. This is a nursery. There you can barely see the edge of a production area, which this I think was a 14-acre wetland that was treating about 200 acres of production. And it worked very well. They weren't having any issues with compliance of nitrogen or phosphorus release into the environment. They were meeting their targets and their goals. Flooding wetlands are a newer technology where if you have a retention reservoir and you're having issues with water quality or algal blooms and some undesirable plants, floating wetlands are one of these options that may actually work to help you manage water quality within a reservoir without taking land out of production for that purpose. And what happens is that you have the plants suspended above the water column, you have the shoots above it, the roots extended below, sort of like this picture that you see the top right, and the roots are extended below, and there's a lot of surface area actually within the water column for microbial communities to colonize, and the microbial communities along with the plant roots. The plants are where helping filter particulate or sediment out of it and absorbing nutrients and transforming nutrients. But there's also provision of habitat for wildlife. So if we're thinking stormwater applications, that actually may be ideal unless it's Canada geese, and then that's a whole different that's a more, can we get rid of them? But then if we're thinking in terms of nurseries, can we use floating wetlands as secondary production areas, or to produce plants that are pretty bulletproof, that, you know, we can grow them in the wetlands for 8 weeks, pull them out, or for 3 months, clean our water, pull them out, cut the roots off, stick them in a pot, grow them for 8 weeks, and sell them. And we have, and one of my PhD students did some of that work, and it actually does look feasible with a return on investment of where you're breaking even and after 2 years, and then you'll start making money on the floating wetland investment. But ideally, when we think about recycling water and managing water on farm, any options that you choose for recycling water are really based on what do you have actually the economics or the capacity to invest? So how much is it going to cost? How effective do you need it to be? And then we can really customize any treatment technology to what your goals are. So if we have a production area that we've figured out, we've dialed in the irrigation system, we can figure out how to put in a carbon wall or a bioreactor, which is basically you dig a big hole, put a liner in it, and stick some wood chips in it, and then let water start to flow through it. And depending upon your flow and your retention time, you can get rid of some pesticides. If you want to look up Dr. Tom Fernandez's work and Damon Abdi, they've shown some high efficacy with fast flow rates. Or if you're wanting to get rid of nitrogen with less effort, then you let the water stay in those bioreactors for a longer period of time, and nitrogen can be removed. Or you can have water flow through the bioreactor and then through a vegetated channel to clean it further, or a sediment catch basin, or a constructed wetland, or a floating wetland. And then you have your sequence or your sort of treatment train of ponds, where you have a dirty pond where you're using a floating wetland to clean the water, but also potentially as a secondary production area, to the next pond, to your clean pond, where you have a lot of other treatment options. And in thinking about this, it's really, let's do a case study to kind of show you what's feasible and what has been done. And this was done in California. So Altman Specialty Plants, they had 157 acres in 2016. 53% of it was outdoor, and about 40%, 50% is again under shade or in the greenhouse. And they were getting water from the Western Municipal Water District and the Metropolitan Water District of Southern California. And so basically their setup is they have a lot of production area here and here. And so that sediment forebay I was showing you, that is actually right here. That one where they designed it very well to be able to be dug out with a backhoe. So they have a remnant pond with some vegetative buffer within here, and then water flows through down another channel that typically was not vegetated until it got to about this point within it. And that was the lower collection pond. And I apologize for keeping these in cubic meters. I did have them in gallons, but I forgot to change that back. And then water is then pumped to an upper storage pump. So they designed a system. This used to be their old pond. They installed this pond, and then they realized they wanted even further capacity to expand it to capture and reuse. So they didn't lose any more water, so they installed another pond at the top. And so what this kind of looks like is water can flow off the production areas and then flow through into that remnant pond where that vegetative buffer is, and then down that water channel to the lower collection pond. Once it's in the lower collection pond, it's pumped to the upper collection pond, but it goes through a series of rapid sand filters, and they actually acid inject to sort of manage pH before it goes into the upper pond, from which it's pumped, excuse me, and they inject chlorine dioxide to sanitize the water so there's no plant pathogen issues, and then it's applied as irrigation. And so when doing the cost benefit analysis of this system, they figured out how much it actually would have cost with no rebates or no grants, because they got rebates from the Water Management District and an NRCS grant to actually fund this work. And it cost them about $1 million to actually install everything from the irrigation reservoir to all of the filtration equipment that was needed. With the subsidies that they were able to get, their net cost was about $360,000. And their estimates of lifetime last from 10 to 20 years before they'll have to start replacing any of the components. But so that, yeah, they almost had $670,000 of subsidies because the water management district wanted them to recycle more water and not just have a once through and release of water. So in 2014, they used a little over 1,000 acre feet of water, and it was 100% from the water management district with nothing recycled. In 2015, after they installed that reservoir, the upper reservoir, they used 1,100 gallons, and which about 63% and was from the water management district and 37% recycled. Again, to 20, about 50-50 recycled or from the water management district. So their water is expensive. So $950 an acre foot, or about it cost them $1 million a year just to get water. So when they were able to recycle it, even if they didn't have the subsidy, that cost went down to about $300 per acre foot, $300 to $395 per acre foot of water from $950 per acre foot. And with the subsidy, it went down to $140 to $170 per acre foot of water because they're recycling it. So the economics of the system paid back pretty quickly. So their cost of water ranged from $750 to $860 without the subsidy, and $650 to $770,000 with the subsidy. So they saved in 2 years $800,000. And if you look back at their initial investment, they invested $1 million. Well, with their subsidies, they invested $400,000. So they made their money back in 2 years with just water savings. Their break-even point without rebates and grants, since they had to use 54 million gallons of water, that was 14% of their water use. Or with the rebates and their subsidies, that was 5% of their water use on a given year. So if water costs you enough, some of the infrastructure that enables recycling can give you a pretty fast payback time. So just sort of things to think about and to consider if you want to recycle water is the first thing that I would think about is water security and sizing that retention reservoir for your maximum stored water capture when allowed, so that you can extend your irrigation water. This allows you to not only have water security, but it also allows you water treatment options because your reservoir in and of itself is serving sort of as a treatment area for water. So the longer water is held within the reservoir, the better off you are. Captured irrigation return flow can safely be reused if site-specific treatment technologies are installed. So once you know sort of the constituents of the irrigation return flow, whether we're talking nursery or landscape, we can sort of develop those site-specific treatment practices that actually enable effective reuse. And I harp on floating wetlands because it's one of my favorite research areas in my lab. But the biological treatment technologies are effective, but I will say they are site and contaminant specific. So this is not something you can say, well, I think I want to do this because I want to get rid of a pesticide, let's say glyphosate. It may or may not work. So we'd have to really think about the chemistry of whatever contaminant you want to get rid of so that we can pick a practice that will actually be effective. Because the last thing we want to do is pick a practice and it not work for what you want it to work for. And then that final take-home message is recycling water can save money when your water costs enough. But it can also sort of buy you some goodwill within the community. If they're seeing you're growing plants that they want for their landscape or for food, and that you're also being conservation and environmentally focused, and you're recycling water because you don't want to release contaminants in the water, and you're helping to treat that water before it's released. So there's a lot of sort of intangibles in the recycling realm that we're just starting to delve into, the sort of the social impacts of recycling water. Some of those are people like them, and some of those are people may not like them. But it's all in getting our message out there and helping formulate it so that it is wider accepted. And what again was concept one? Concept one was size irrigation retention reservoirs for maximum stormwater capture when allowed. So that's thinking about if you know the frequency of sort of like a 5-year storm or a 10-year storm or a 100-year storm, and you can actually size a retention reservoir to capture that projected volume, then you're over engineering your system, but you're also enabling capture of larger volumes of water that would otherwise not be captured if it was undersized. Okay, and that is all I have for this. I have some resources for you as well. Feel free to email me, but I will stop my video so that if you ask questions, you're welcome to do so.
Hi, thank you, Sarah. And that was a wonderful presentation. And I hope people here have questions. And we do have 10 minutes to ask questions and get answers. So if you have any questions, feel free to type your questions at Q&A. And like I see a lot of my name here, so if you want to avoid that next time, please register and put your email, and then when you use the Zoom link from that email, then your name will show up. But yeah, I'm sorry for that. And yeah, if you have any questions, feel free to put in here.
I know I threw a lot of information, so
No, but
there's no harm, no foul if you don't want to ask a question in front of the group. But don't think it's there's no question that's not a good question, because someone else may have the very same question and just be too shy to ask.
Yeah, and right now you can actually ask it under my name, so nobody would still know you, right? So, but anyway, yeah. if you have any questions, ask right now. If you think of some other questions later, maybe after 2 days, after 5 days, send me an email or send Sarah an email, and she will be answering it. But if we do not have any questions, okay.
So there were some questions in the chat. So Q&A, I'm going to answer one live. Let's see. So Shatal, you asked a question, and I don't know who the Shatal who asked it was, but I'm interested in the smaller version of, I'm assuming this is the retention reservoir, and it looked like feeder troughs with piping. Where can we define the design and research on this? So if you look at the webinar, the last slide that I showed, which I'll put back up briefly, and the land grant press article that I showed briefly, that was, I'm trying to get back to the right. Okay, there we go. The first article here, this Yazdi, is a critical review of irrigation retention reservoir performance and design considerations. And it's you can just download this article using this link. And Grant Press article also walks through there, but it's a little potentially more accessible language. But the Journal of Cleaner Production is sort of the peer-reviewed journal article on this. Russell had a question, which was, have we looked at tilapia fish to help remove solids? We have, well, I haven't, but I've seen research where it has been done. It's typically done for algae management where I've seen it, and it tends to work. It depends how cold your winters get as to whether they're overwinter. You really don't want them overwintering. You'd rather have them do their job and then pull them out and eat them. But that's, up to you. And then Heidi had a question in the chat area, is what are some impacts of recycling water when water is not released downstream? What do you mean? Sorry. So impacts of recycling water in that you are continuing to recycle your water and your contaminants on farm. That's not necessarily a bad thing, because typically the pesticides that you've applied, you actually wouldn't mind if they were reapplied sort of as a low-level drench along with the fertilizers. in that instance. So you actually may be recycling some of the agrochemicals on farm and not actually having it leave your operation. So you're reusing those rather than losing them if that water were released off farm.
And then Kim,
Okay. So Kim,
what are
Lambert
your...
growers in West. Go ahead. Were you going to read it to me?
Yeah,
That's
I can
fine.
read it to you. So
Yeah.
this is Kim from Lombard Growers in West Valley City, Utah. What are your thoughts on urban interface? We are surrounded by people, apartments, etc.
So this is where capturing your runoff and treating it in some way, shape, or form before it's released is really important. But it also gets down to that landlocked nature and finding ways to do it that don't take up space. We have some. So, and can you? What's your water source? Do you have any way to capture water? I would need more information from you to give you good advice on that. But
Kim,
culinary well water in an in an irrigation ditch.
So I think
I mean, yeah, you are in you're in one of those hard situations where you're landlocked, where you have a lot of competing uses and users around are probably looking at you pretty critically and asking you, what are you doing and how are your practices impacting my daily life? This is hard for me to answer on the spur of the moment. There's things that I would say I think you could do, but email me and CC Chital, and we can come up with something that may actually help you. And I'd be happy to do that. Yeah.
Awesome. And Katie Wagner, I'm sorry, Katie, I should have invited you as a panelist. My email's not working since an hour, so I don't know what's happening, but she says, I'm familiar with the use of constructed wetland in the East too. For example, remediate mining sites, but are constructed wetland used in Western states? So are the constructed wetlands?
I have seen constructed wetlands used in Western states, and actually many times they are actually associated with wastewater treatment plants. So if they're needing a sort of tertiary treatment of wastewater before it's released, they run it through a vegetated buffer or the constructed wetland where they can help get additional treatment of water without some of the expense associated with some of the energy intensive wastewater treatment practices. So yes, they are used. I've seen them in Oregon, I've seen them in Washington, I have seen them in California as well. So I think that it's something that's feasible. Just design would be the question.
And Jacqueline asks, is there a list of plants that are good for floating treatment wetlands?
There is a list of plants. Now, I will say that they are plants that have been vetted for the East Coast. So what I would probably, how I think about floating wetland plants are you want wetland plants. So I would kind of pick some of your native aquatic plants or wetland plants that are good for Utah. If you have some of those, and I bet you do.
We do.
And think about which of those one could use. Now, the beauty of a floating wetland is that you can play with the plants. And we put some grass species that are not typically grown in water in floating wetlands. And as long as we keep the crowns above that water surface so they can dry out, the plant lives. So if you have Carex species, some Juncus, Pontedarius, Sagittaria. But if you look up floating wetlands and Clemson University, there's a lot of resources.
And I would also like to tell Jacqueline, so we are planning to do research on 3 different wetland plants to see how it can take up phosphorus and nitrate. So, and those are all locally here in Utah, and we chose it from the PDF. There's a PDF titled Wetland Plants of Great Salt Lake. So those are the plants that like here in Utah and they can be grown. And this was a place where we went to look at the plants, and then we did more paper review and selected the plants. So if you look at these PDFs and Google it out, I think you'll find many.
That's really cool. And And some of the opportunity there is if you can grow plants that are sort of native to the region and get numbers bulked up, then you can have them available for sale or for restoration purposes and other applications. So there's a potential for second uses and other uses.
But you need to consider the invasive. You need to also understand that there are a lot of invasive plants that are wetland plants, so you need to avoid using those plants. And so I think that is all the question that, let's see, that's all the question that we had, and it's 2:30. So thank you so much, Sarah, for taking your time to give this presentation. It was nice. Thank you, all the participants, and this video will be recorded.